In this illustration, we intend to calculate the stress due to temperature increase using the Abacus software and the analytical solution, and then compare the results obtained from the Abacus software with those of the analytical solution. As you observe in this picture, the model includes rod AC, cylinder BD, and rigid bar CDE. The length of rod AC is equal to 0.9 meters, cylinder BD is 0.3 meters, and that of bar CDE is 0.75 meters. The cylinder BD is made of brass and the rod AC is made of steel. Actually, this problem has been selected from Mechanics of Materials book, and you can observe this problem in this picture. The statement is that the temperature of the entire model is 20 degrees Celsius. Then the temperature of the brass cylinder increases to 50 degrees Celsius, while the temperature of the steel rod remains constant at the same temperature of 20 degrees Celsius. The purpose is to calculate the stress in the cylinder BD. Actually, we will solve the problem using the Abacus software and then compare the results obtained from the Abacus software with those of analytical solution. Here also you can observe the process of solving this problem using the analytical solution. First, I intend to define the properties of brass. Actually, as explained in the book, the cylinder BD is made of brass. I click on Mechanical menu, then on Elasticity and Elastic. The Young modulus of the brass is equal to 105 gigapascal. I will enter the Young modulus of that equal to 105,000 megapascal. The Poisson ratio of brass is equal to 0.3. I click on Mechanical menu, then on Expansion. The expansion coefficient of brass is equal to 20.9 multiplied by 10 to the power of negative 6 per centigrade. OK. I click on Create section. Here, select Beam and then Beam again. Continue. Here, I'll select Brass Material. I will click on Create Beam Profile. Here, select Circular and continue. As explained in the book, the diameter of brass cylinder is equal to 30 millimeters. So, I'll enter its radius equal to 15 millimeters. OK and OK. I will click on Assign section, select Cylinder BD, Done, and OK. In the next step, I'll click on Create Predefined Field, select Initial Step, then Temperature, and continue. I will select the whole of the model. Done. As explained in the book, the temperature of the whole model is 20 centigrade. I will enter the temperature of the whole model equal to 20 centigrade and OK. I click on Create Predefined Field again. Select Step 1. Here, select Temperature and continue. As explained in the book, the temperature of the brass cylinder increases up to 50 centigrade, while the temperature of steel rod remains at the same 20 centigrade. Here, I will select the brass bar, done, and enter its temperature equal to 50 centigrade. It actually means that the initial temperature of the whole of the model is first 20 centigrade, and with passage of time, the temperature of cylinder BD will increase up to 50 centigrade, but the temperature of rod AC remains at the same 20 centigrade. This problem has been solved in Mechanics of Material book using the analytical solution, and here the process of solving can be observed. To solve this problem, first we should draw the free diagram of the model. Then we should write the moment about point E, and doing so, the relations of RA and RB will be obtained. In the next step, the change of length due to temperature increase has been calculated, and the increase of temperature is actually equal to 30 degrees. And here you can observe the change of length as a result of temperature rise. In the next step, the relation between deflection of point D and point C has been written, and here this relation can be clearly observed. In the next step, the formula of deflection of point C has been written. RA is the force having been applied to rod AC. L is the length of rod AC, that is equal to 0.9 meters. A is a cross-section of rod AC. And E is the Young modulus of rod AC. Here, the deflection of BD has been calculated, in which RB is the force having been applied to cylinder BD, L is the length of cylinder BD, that is equal to 0.3 meters, A is its cross section, and E is its Young modulus. Eventually, by simplification of relations, RB will be obtained, and as previously mentioned, RB is the same force applied to the cylinder BD. Finally, the stress in the cylinder BD is equal to 44.8 megapascal. Here, we intend to obtain the stress in the cylinder BD using the Abacus software. I will click on Create XY Data, then ODB, Field Output, and continue. Here, I will select Unique Nodal, then S11 or the same axial stress. Here, I will select 1 point from cylinder BD and click on Save As. Here the diagram of stress can be observed. As you observe, the stress in the cylinder BD is equal to 44.75 megapascal. Actually, the stress obtained from the Abacus software is equal to 44.75 megapascal, and the stress having been gained by the analytical solution is equal to 44.8 megapascal. As you observe, the results obtained from the Abacus software are so close to those gained from the analytical solution. Here we intend to calculate the difference between the results gained from the analytical solution and those of the Abacus software. As you observe, the difference between the results of the Abacus software and the analytical solution is about 0.1%. Actually, the results obtained from the Abacus software are precisely concordant with those of the analytical solution. The next point we intend to calculate is compressive or tensile feature of the stress. As you observe in this picture, force has been applied to the cylinder BD in compressive form, and the negative sign in the Abacus software indicates that the stress is in compressive form. Regarding this matter, the results of the Abacus software are also concordant with those of the analytical solution, and stress is in compressive form in both cases. The next point we want to calculate is the force applied to the cylinder BD. The force having been applied to the cylinder BD gained from the analytical solution is equal to 31,700 newtons. Now we intend to calculate the force applied to the cylinder BD using the Abacus software. To do so, I will click on Create XY Data, select ODB, History Output, and Continue. Here I will select RF2, that is the same reaction force directed at y-axis. Then I will select this point and click on Save. The force having been applied to cylinder BD has been obtained from the Abacus software and is equal to 31,633 Newton. As you observe, the results obtained from the Abacus software are extremely close to those of the analytical solution. Actually, the force obtained from the Abacus software is equal to 31,633 Newton, and the force gained from the analytical solution is equal to 31,700 Newton. The next issue we want to survey is the direction of the force having been applied to cylinder BD. As you observe, the direction of the force applied to cylinder BD is upwards. As it can be observed here, the direction of the force is upwards. Actually, the results obtained from the Abacus software and of analytical results are the same and identical. The next point is the force applied to the rod AC, which, as you can see in the Abacus software, the direction of the force is downwards, and the direction of the force applied to the rod AC is also downwards according to the analytical solution.